All right, guys. So what I'll do is I'm gonna continue with what we were doing, and let me see. Okay, so let's continue, and this time let's work on this example, example number 7. All right. So what we have here is we have this pendulum, right, is moving in a vertical plane, right? So we have this bob basically, or this mass is connected to the pendulum, and it's initially moving with a vertical velocity. So at this point, it's actually moving with a vertical velocity of 6 meters per second. 1 theta is equal to 0. So when it's here, it's moving up. We would like to find the angle theta, right, where the tension in the cord becomes 0. So at some point, as this guy goes up, the tension in the cable will actually become 0. So I can try to draw it to further illustrate that for you guys. Okay. So let's do it here. So basically, this is what we have. Okay, so this is the weight that we have. And at this point here, basically, it actually has a velocity of V0. All right. And, you know, as a result of the velocity, this guy is going to go up, up, up. But maybe at some point, it will start doing that, right? Might be too heavy or whatever. Okay. So at some point here, you will actually have what? The tension in the cable, tension will actually go to 0, right? We need to find this angle, theta, right? Let's call that angle theta 0. Okay. We need to find that angle. So we have to do a free body diagram, and then when we do a free body diagram, we're going to do it somewhere in the middle, right? Somewhere in the middle where we have all the forces, and then we're going to look at the accelerations, and then we're going to try to see how we can actually compute the angle when this guy goes to, when t goes to 0. Okay, so let's do a free body diagram on this. How does the free body diagram look like? What do you think we are going to have on that free body diagram? Right? So this guy here. Maybe can someone help me out here?
Yes, the weight.
Exactly, bravo. So we have the weight.
And the tension.
Okay. So we have the weight, and then we have the tension. Exactly. Right? And then we know this guy will be making this angle. Theta. Okay, to make it more clear. How about on this diagram? What do you think we have? On this guy.
Normal acceleration.
Normal acceleration, exactly. So how does the normal acceleration would look like in this case?
mv squared over r.
mv squared over
the same direction as.
Yeah. So long as this guy is along the curve, مظبوط, it's following a perfect circle, then we have mv squared over r. Check. Okay. What tension will goes to 0 when this guy is no longer following a pure circle. مش هيك؟ So long as the tension is greater than 0, we know this guy is following a pure circle. مش هيك؟ It's basically trying to pull it. But when, you know, so long as we actually have tension, right, then this guy is definitely correct. Is there any other accelerations that we have or no?
It's slowing down, isn't it, doctor? The speed, yani?
The speed will go down. Yes, exactly. Yep. So do I have any other acceleration on here or no? Okay, if you look, we know, if we look into the relationship between the forces and the acceleration, right? So this tension and then, you know, this component of the weight, مظبوط, هذا component of the weight along this direction will actually be equal to this, right? So T plus mg, for example, right? Whatever that angle is. If I actually do that here, this angle is equal to what? This angle here? It's theta. Exactly. So T plus, let's say, mg sine theta has to be equal to mv squared over r, okay? But how about this component of the weight? The component of the weight that is along this line. What is that doing? Higher component of the weight. It has to have an acceleration in the same direction, okay? We know F is equal to ma. That's what Newton told us, like, you know, 500 years ago. So F is equal to ma. We cannot have a force without an acceleration. is a net force. We cannot have a net force. So هون عندنا it looks like we have a net force مش هيك along this axis. So therefore we must have شو A مظبوط.
Acceleration.
Yeah, exactly. We have a net force on an object. This object here is, from pure physics, this object is in space, basically, right? You have no force acting on it, right? So it must have some acceleration on this end, right? So we're going to do the
In the
same.
same direction of mg, doctor.
Exactly. It has to be in the same direction as mg. مظبوط ولا لا? Yep. Okay, so here we have m, and I'm going to call this at because in reality, it is actually a tangential acceleration, right? So we have normal acceleration and then we have a tangential acceleration. This has to be present. Why? Because this, we actually have a positive a component of force that is actually along this axis. So there must be an MA. Okay, deal. Okay, great. So what next right now? The question is we need to find the angle theta. How can I find the angle theta?
Now we sum the equations in one direction.
We can
We sum the equations in tension, for example.
Okay. All right. So okay. So let's sum the forces along the tension. Okay. Because we need at least to know, at what value of the tension, right? Or what value of theta will actually make t to be equal to 0, right? So if I sum the force along the tension, what am I going to end up with?
Minus t.
Yep. So minus t, okay.
Plus mg sine theta.
Plus or minus?
Minus.
Exactly. Why? Because this arrow is actually pointing against the direction which I'm assuming to be positive, right? So minus mg sine theta. Okay, very good. It's going to be equal to what? How about on here? كمان minus, right? So minus
mv squared over r.
mv squared over r. Okay. So if I were to actually find the angle theta, right, I need to find this when t is equal to 0, right? So I'm trying to find when theta is equal to 0. So if I actually, how can I find that? So when t goes to 0, I can literally solve that, right? So if t is equal to 0, مظبوط, I can use this now to find sine theta, right? Okay. For a given theta, this guy could actually be 0, right? If I actually, so I can, even multiply this by positive. So I'm gonna be here. So 0 plus mg sine theta is equal to mv squared over r. So how can I find the angle? It's going to be this guy, right? So sine theta was both. So m and m will actually cancel out. So sine theta is going to be equal to v squared over gr.
G times r, yeah.
Me, exactly. So theta is going to be equal to sine minus 1 of v squared over gr. You guys agree?
Yes, doctor.
Okay, but what is the issue here, though? We have a small issue. This velocity, what velocity is that?
It's not the. Is it the initial velocity?
No, that is not the initial velocity. We're doing a free body diagram at any instant at some, just random theta, right? And at this random theta, basically, we have mv squared over r, right? So this is the velocity of the block when at that particular value. So how can I relate the tangential velocity to the initial velocity, given that I have this acceleration at? All right, does it make sense? So this theta هلا that we just solved, right? So if this condition is satisfied, right? If theta is equal to v squared over gr, right? Then at this angle, basically, I know we're gonna have some escape, right? Then this tension will actually goes to 0, right? And a tension in the cable cannot be negative. Does it make sense? So when this guy is equal to this guy, then this guy would be equal to 0, right? So now we solved for theta. But how can I actually find the velocity along the curve, right? So I know if I'm starting here with some velocity v0, right? As I'm going up, my velocity is going to change, right? How can I find the velocity at this instant? Well, here's what we have. We have the initial velocity, مش هيك? But we also have the acceleration. So if you have initial velocity and then you have the acceleration, you should be able to find the velocity at this position. Check. Okay, we need to find the acceleration. How can I find AT?
مش بنعمل summation of forces كمان بس in this direction.
Bravo, exactly. So all you do literally just sum the forces, and what I'll do is I'm gonna sum the forces. Okay, here you go. So I'm gonna sum the forces along this direction, right? Because I'm interested in finding AT. What do you think AT is gonna be equal to? So well, let's do it, right? So if I sum the forces along AT, what am I gonna do here? What am I gonna get here?
minus mg cosine theta.
Yeah, but under the positive direction is along AT. So it's gonna be mg
Okay, positive. Yeah.
cosine theta, my هيك, is gonna be equal to what?
M80.
Bravo, M80. So M and M will cancel out. So I have AT is going to be equal to G cosine theta. Okay, so now we actually have the acceleration along the curve. All right. So if I have the acceleration and I actually, how can I find the velocity?
We integrate.
You integrate, exactly. But what equation do you have to use? If you guys remember, we have AT, right? ATDS, right, is equal to VdV. You guys remember that? Right? So here, the acceleration is actually provided to us as a function of the position, right? So all we have to do is basically do this operation, right? What is AT? AT is going to be equal to what? G cosine theta, مش هيك? What is DS in that case? Can someone tell me what is DS?
D theta.
I'm sorry?
D theta.
So ds is basically just a tiny element that you actually go here. So ds is going to be equal to r d theta, مش هيك? So if this is ds here, right? And this guy is r, so ds is going to be equal to r d theta. Okay, so at, which is already g cosine theta, مظبوط, multiplied by ds, which is r d theta, is equal to vdv. Okay. So I need to relate the velocity with, so I know the initial velocity is V0, right? So I need to find the velocity at any angle theta. How can I find the velocity at any angle theta? So I want to integrate that, right? I want to integrate this guy from V0 to V. How about this guy? I'm going to integrate this guy from what? From 0 to theta, right? Okay, so I know the acceleration is ATDS is equal to VdV, so I'm going to integrate these two. What do I end up is if I actually integrate these two? What is the integration of G cosine theta r d theta? It will be G sine theta r. مش هيك? Integration of cosine theta is r, G r sine theta.
Yes.
Okay, and this guy here is going to be equal to what? V square over 2, مظبوط, from V0 to V, which is equal to V square over 2 minus what? V0 square over 2, correct?
Yes, doctor.
Okay, so now we need to know V square. What is V square? V square is going to be equal to, so I'll multiply the whole thing by 2, so it's going to be 2G R sine theta plus V0 square. So نحن هلا اللي عملناه هو we are relating the velocity at any point along the curve. So as the ball basically goes up, we have the velocity in terms of initial velocity V0, right? So whatever the initial velocity that you have, right? And whatever theta you are, you can actually find the velocity. And then we got that by knowing that we know the acceleration along the curve is actually a function of the position. And we've said since day one, when acceleration is a function of the position, you will use ADS to find VdV, right? To find the velocity, or to find the relationship between the position and the velocity. This is the relationship. Okay, now what should I do, guys, now? What is the next step now?
So once we find V here, we plug it into the equation we found before.
Bravo, kidding me. Exactly. So I have this V squared. I'm going to actually plug it back here, right? Okay, so let's come back here. So we said initially, sine theta will be equal to v squared over gr when retention goes to 0. But we also know v squared is equal to how much? To gr sine theta plus
Plus
v.
V0. Yes.
So I'm gonna take this guy. It's gonna go here. So sine theta, I'm gonna multiply it by gr هيك to simplify it is equal to v squared اللي هي هون 2 gr sine theta plus v0 square. Okay, so I need to find we need to find sine theta. I think this has to be minus actually, right? When we integrated this guy, right? From 0 to g, right? When we integrate g cosine theta, it will be g sine theta, right?
Should
And-
say positive. Yeah.
I'm sorry?
It should say positive. It's not. Yeah. It's correct, Mark. Till now.
ما سمعت.
لا, I'm just correcting you. You said cosine to sine should be negative when we integrate. That's correct. You did it correct.
Yeah, it is correct. So here we have v squared over 2, right? We're starting at v0 and we're going to v, right? Okay. Okay, we have one thing here though. L80 هون is g cosine theta, right? But when we're actually doing that, the acceleration is opposing the movement هون, right? So the AT هون is actually opposing the movement, right? So when we are doing AT times ds, remember this actually has to be on a negative, right? Why? Because the AT is actually opposing the movement. So this guy actually has to be minus, right? Why? Because we're actually doing AT ds, right? Well, acceleration هون is always in the opposite direction as a ds. So if ds is increasing, AT is always negative, right? So when you are doing AT ds here, you have to recognize that AT is in the opposite direction as ds. So this guy here is actually this guy right here is actually negative. Okay, as a result, when you integrate that, right? So the negative will actually carry on. So minus g sine theta r. Okay. And this guy has to be minus, which makes sense, right? Why? Because as your angle theta increases, مظبوط, initially for theta equal to 0, v is equal to v0, right? But if theta increases, your velocity will actually reduce, right? Because the acceleration or the gravity is basically pulling you downward. So this is the right value for v squared. And this guy has to be minus here, right? This is what we did earlier, right? So v squared is equal to minus 2gr sine theta plus v0 squared. And this guy here is going to be minus, right? So now I can actually bring that over here. So it's going to be 3 gr sine theta is equal to v0 squared. So now we're good. So sine theta is equal to v0 squared over 3 gr. So now basically we have obtained that. So remember initially we had what? Sine theta was equal to v squared over gr. Now sine theta is actually equal to v0 squared over 3 gr as a result of using the initial velocity and not using the current velocity. Okay, so how do I find theta? Theta is going to be inverse. Exactly, inverse sine of that. Okay, I have a question for you guys. Okay, and then this is the last question, and then I'll let you go. If you're on the exam, right? You're doing your best. You're solving the exam, etc. You plug in these numbers. I gave you some values for v0, g, or etc. You plug these numbers, and that number turned to be like 1.2. What is theta? Okay, so you're on the exam. I gave you some initial velocity. I gave you the radius of it, and I told you you're on planet Earth. So unfortunately, you cannot change g, right? You're fixed to 9.8. What happened? Like how you can find theta? Like inverse sine of 1.2 is equal to what?
On my calculator, it's giving me math error, so it probably doesn't exist.
It doesn't exist, exactly. So how would you interpret that physically? Like, you know, if
So
you
like this, يعني this outcome is impossible to happen. Maybe I think.
is impossible. يعني okay, if we go back to our example
and
هون,
tension ما بتصير zero.
tension will never be zero, exactly. And the velocity تبعك is too much. Initial velocity تبعك is too much. So by the time it's actually at the top, it's impossible. مظبوط. So تتا هون صارت 90 degree والتنشن منا zero. So كفته برمت, right? So it's impossible أن movement يكون the movement will result in you know, in tension being negative, right? So the tension is always positive. So basically the tension always have to exist, right, to counter the inertial force. Okay, so this is the interpretation of it. Okay, guys, great. Thank you for attending, and all these are going to be posted on, you know, on our Blackboard for you to be able to, you know, revise that and then review it. Okay. Thank you. Bye bye.
Doctor,
Thank you, doctor.
Yep.
for the exam, should we scan the solution and send it to you afterwards or no need?
Yes, you should. You should.
Okay, doctor. Thank you.
All right. Bye bye.